All right, we're at section 13.3, analysis model particle in the gravitational field. Now, Newton's law was very, very successful, um, but people had a hard time understanding it. I mean, people were used to force, um, contact forces. We've discussed contact forces and field forces. This was a new concept to them. They didn't have the idea of field forces, um, but they knew that Newton's equation was correct. It was used to account for motions of comets, deflection of the Cavendish balance, orbits of binary stars, and rotation of galaxies. So it was um, confirmed that it was correct, but his contemporaries and successors found it difficult to accept the concept of forces acting at a distance. And then an approach was uh, tried where it discussed a gravitational field that exists at every point in space. Um, so the uh, the way, and we'll do this with the uh, electricity and magnetism too. We're going to have a test particle, and this particular test particle is m0. It's just the amount of mass isn't important, but we just put a test particle in a gravitational field, and the gravitational field is the force that it experiences from that gravity divided by the mass of that test mass. Um, so that force is equal to mg. Um, we'll know that that any mass will experience a force by that gravitational acceleration um, when that mass is placed in the gravitational field. So this concept of gravitational field came up. And so here's an image, the field vectors. Now this is a large scale view of the Earth. So the field vectors point in the direction of the acceleration a particle would experience if it were placed in the field. The magnitude of the field vector at any location is the magnitude of the free fall acceleration at that location. And if you look at the details, you can see that on the outside ring of these arrows, they're not very long, but as you get closer to the Earth, the arrows increase. If you're in an area that's close to the surface of the Earth, as in B, it's going to be pretty uniform for limited heights, and it'll all be directed downward. Um, so the G is equal to this, the force exerted on the test mass 0, and that's equal to minus G, mass of the Earth, times the radius squared in the unit R direction, the unit vector R. And you can see that it's negative because it's downward towards the surface of the Earth. Um, so the particle in the field, um, we have examples. We look at an object of mass m near the Earth, uh, near the surface of the Earth. It has weight, which is the result of the gravitational field established in space by the Earth. A planet in the solar system is in orbit around the sun due to the gravitational force on the planet exerted by the gravitational field established by the sun. The gravitational field of the sun is what keeps the planets in motion. Um, and so we have other examples. An object near a black hole is drawn into a black hole, never to escape due to the tremendous gravitational field established by the black hole. So this concept of field will return to again in electricity and magnetism. A charged particle in the presence of an electric field, if it's a positive particle, it'll be repelled. If it's a negative particle, it'll be attracted to the source of the positive electric field. So G is equal to the gravitational force divided by this test particle. For a general mass, the gravitational force is equal to that mass times the gravitational field at that point. Okay, and next we're going to talk about 13.4. We're going to go to Kepler's law and the motion of planets.